Hi, this is the Flight Readiness review video that Suas Anadolu team has prepared for 2018 SUAS competition from Turkey. This presentation video demonstrates to SUAS Anadolu team's unmanned aerial system which named Zafer, created by the cooperation of undergraduate students from Faculty of Engineering and Aviation in Anadolu University. Hasan Mertcan Özkan, the team captain, primary flight controller. Nuri Özbey, image processing operator. Murat Tulgaç, obstacle avoidance operator. Bilgin Selimoğlu, secondary flight controller. Yusuf Aksoy, interoperability operator. Ogün Görkem Kısıkaya, onboard system operator. Alper Mandacı, Flight Mechanic. Derya Kepenek, Safety Inspector and Liaison with Judges. Kadir Çelik, Safety Pilot. Muhammed Taşkıran, Assistant Safety Pilot. And Zafer. For the 2018 SUS competition, a UAV is needed to meet all task requirements which will be attempted within a limited time in cost, budgets and resources, according to the team capabilities and performance. In order to get the UAV which has desired properties, based on the experience gained in the previous years, it was decided that to participate in the 2018 SUS competition with a new air platform named as Zafer that is designed by the SUS Anadolu team. Zafer is designed to be completely modular in order not to encounter again with transport and custom problems that have arisen over the past years. Zafer is inverted V-tail model which provides more control with less servo motors. In past years, due to limited space in Trainer 60's fuselage, working on it was both frustrating and time-consuming. So, Zafer fuselage was designed as wide enough to hold the payload and structural joints, and it's made by carbon tube and plywood composite structure to provide enough strength. The wings are able to generate enough lift for carrying all mission equipment under chosen flight speeds. Moreover, to complete each mission task, subsystems were designed, tested, and placed on Zafer. These are autopilot, imagery, communication, and structural subsystems. These subsystems consist of several hardware and software components such as autopilot system for autonomous flight, camera and onboard computer for imagery, long-range antennas for communication, triggering and safety mechanism for air delivery. During the preparation period of the 2018 SES competition, over 25 flight tests have been performed. The total duration of this flight test is approximately 40 hours, and in this flight test, all the competition missions have been carried out until the test results have achieved sufficient success. As a result of this flight task, autonomous takeoff will be attempted with high confidence. Autonomous flight will be attempted with high confidence. Autonomous landing will be attempted with high confidence. Waypoint captured will be attempted with high confidence. Airdrop will be attempted with high confidence. Stationary obstacle avoidance will be attempted with low confidence. Object geolocation will be attempted with medium confidence. Object characteristic will be attempted with high confidence. Actionable intelligence will be attempted with medium confidence. However, moving obstacle avoidance will not be attempted because the prepared algorithm hasn't passed the security test yet. Also, a fixed target will not be attempted due to the bulky size and the weight of the camera and its required gimbal. The Supreme model and unit testing were adapted to development of Zafer. Up to now, 3 prototypes have been designed and tested. For each prototype, we first applied unit testing to each subsystem components on the ground. And if the components passed the tests, they were integrated into Zafer, and then compatibility tests were performed on the whole system. After being sure that all subsystems working well together, the flight tests were performed to see if the results meet the requirements of the mission tasks. In previous years, Suas Anadolu team was not able to complete full autonomous flight, which include autonomous takeoff landing. During the preparation period of the 2017 SES competition, the first aim of the team was determined as to achieve the full autonomous flight without any interrupting by safety pilots. Last year, for the first time, our team was able to complete full autonomous flight successfully with Markut. In this year, including prototypes, over the 15 flights were performed in autonomous mode after the ensured airworthiness of Zafer. Also, according to the characteristic of Zafer, autonomous takeoff and landing parameters were upgraded based on the experience gained in the last year. To improve the performance and the stability of the autonomous flight, takeoff and landing, additional sensors such as rangefinder and airspeed sensor were used. To increase the accuracy of the flight controller, an additional sensor were tuned with the help of the mission planner interface. After analyzing the specification and capabilities of Zafer, full mission flights have been started. During these flights, the safety pilot mostly has taken the control for only general controls, takeoff, landing, and emergency phases for about 10 minutes in each flight. During the preparation process of the competition, over 15 flights were performed in autonomous mode. In these flights, 430 waypoints capture were attempted. 387 of them were captured and 43 of them were missed. The overall waypoints accuracy of Zafer is calculated as 19%. In moderate weather conditions, and as long as the radius of the successive waypoints do not intersect with each other, the waypoint ratio can reach up to over 95% accuracy. In this year, the team is developed a new algorithm which is able to calculate a new path for waypoint capture, search area, and obstacle avoidance whenever there is an intersection point between path and obstacles. Developed algorithm calculate a new path before the flight, and this path will be uploaded to the Zafer before takeoff. For moving obstacle avoidance, many task stages needed to be performed. However, because of some problems which were happened during the construction of the new UAV platform, enough number of safety tasks could not be performed before the competition, and this year, team will not be attempted to do moving obstacle avoidance. At the early beginning of the development process in stationary obstacle avoidance algorithm, Zafer could not be avoided some obstacles which were complexly located. Also, in this created path by the algorithm, some locations were placed at the edge of the flight boundaries. This could be a huge safety problem for the competition. After solving these important problems, the team is focused to increase the obstacle avoidance performance, a simulation which will be created for the testing, including aircraft characteristics. Up to now, 10 tests were performed for stationary obstacle avoidance. As a result, Zafer can be managed to calculate a new path and detected intersection of the path with stationary obstacles. During tests, the algorithm has been able to avoid approximately 69% of the obstacles. During flight tests, thousands of images were captured when Zafer flies at cruise speed, which is about 50 per second, at 200 feet. A frame per second capture ratio were used scanning whole search area without missing any physical lens. In this process, onboard computer system triggers the camera to capture images automatically. Also, this system is responsible for controlling the camera, fetching the data from the sensors, and transmitting them to the ground station. After the images are captured, onboard computer organizes the captured images and gives them a tag according to the instant data from sensors and Zafer's position. After that, these images sent to the ground station with using imagery link, and the transfer ratio from Zafer to ground station is 1 image per second. The resolution of the captured target images is 450 pixels by 450 pixels, and this resolution value is sufficient for the image detection process. Also, the imaging performance was enhanced by the optimizing the settings of the camera. In addition, the image quality was reduced to minimize the image transfer time. During the development of the image processing algorithm, several images were used which are captured at the mission flight in 2015 and 2017. The algorithm was tested with 10 different targets, including the emergent target. The detection algorithm hasn't missed any of the targets, but there was a high false detection rate. However, these false detections can be eliminated with a post-processing before the classification. The classification performance depends on many parameters, including the brightness or the quality of the photograph. According to the error test data, 19% accuracy for the shape detection, 19% accuracy for the color identification, and 60% accuracy for alphanumeric detection were received. Overall, we have obtained an average of 80% accuracy for classification of the objects. During the development of the localization algorithm, there is a vicious sphere to calculate the real-world localization of the target. The algorithm depends on the onboard computer sensors values such as yaw angle, altitude, latitude, and longitude. The last year, our localization performance wasn't good enough. Firstly, we have started the development process with increasing the accuracy of the localization performance. In the beginning of the test, we had only 45% accuracy over 40 images. After increasing the sensor stability, finally we had 60% accuracy over 40 localization images from datasheets. Overall, the accuracy of the localization performance has been achieved up to almost 70% in recent tests by changing the parameters in the calculation. This is the ground station interface, which is designed to monitoring autonomous and manual detection. After detection, the interface sends the detected objects to the judge's server automatically. We can also add new targets with using the manual addition. In 2018 competition, unlike previous years, the payload bubble must explode at the collision and generate water trace on the ground. So, when designing the air delivery system, in order to minimize the cost and time lost, it was aimed at to create the simplest system which satisfying the conditions. After being sure that mechanical components working well, two main tests were performed. The first one was collision test. In this test, without any additional system, the explosion ability of the bottle were tested, and it was seen that the bottle explodes when it falls from the height of almost 13 feet to the asphalt road, or from almost 50 feet to the lawn ground. In order to avoid any surprises, the height of the air delivery was determined to be at least 50 feet. The second one was wind test. In addition to the obstacle avoidance algorithm, an algorithm is constructed to refer to the wind speed and the cruising speed of the aircraft to increase the impact location sensitivity of the payload. Up to now, 11 air delivery tests have been performed. In 9 of them, the bottle successfully exploded. The average aero distance was determined as 38 feet. As the approaching to the end of the preparation period, the team made a score estimate that could be obtained in the competition considering the situation of the prepared systems. After that score estimation, the team achieved several full mission tests to observe flight area performance, then compared the estimated scores with the real mission scores. In those tests, it was aimed to detect possible mistakes during the mission test and to maximize the compatibility between the subsystems. Up to now, 5 full mission tests have been done. Those tests include full autonomous flight, stationary obstacle avoidance, ODCL, and air delivery missions. The possible mistakes were identified and the necessary improvements were made in each of these 5 tests. As a result of this, our mission score increased after each test as expected. Eventually, the team has reached a score which is higher than the estimated score after the 5th test.